Hi there. Welcome. My name is Dan Patterson, and this is a panel discussion on Canada's quantum internet, the prospects and perils. We have a fantastic panel today featuring Francesco Bova, Anne Broadbent, John Lindsay, and Christoph Simon. These are all experts and academics and specialists in quantum computing. Today, we'll talk about quantum information and how the science harnesses the strange properties of quantum physics to perform new kinds of communication and computation. A future internet that uses quantum networks and quantum computers has the potential to enable many new applications for government and civil society. Canada has emerged as a leader in quantum information science, and academic and commercial labs are actively experimenting with quantum networks. And yet, with any great technological promise, there is also danger. Architects of the classical internet did not anticipate the crisis of disinformation, cybersecurity, and surveillance that plague global networks. As we look towards a possible future quantum internet, what are the risks and challenges we should anticipate? How can Canada best position itself to take advantage of its own potential for innovation and quantum technology? This is going to be a fascinating conversation. I'm a journalist and the lone American on this panel, but I'm humbled and kind of fascinated by all of our panelists. I want to start with the basics. I know we've all heard about quantum computing, but I think it's really good to define terms before we jump into a fairly heady conversation. So, Anne, I wonder if we could start with you. What is the word quantum? What is quantum computing, and what is the quantum internet?
Sure. Hi, everybody. It's a pleasure to be here today. What are the basic terms we're going to talk about? First of all, quantum refers to quantum mechanics. You might have heard of quantum physics. This is the physical theory developed in the 1920s and tells us how objects behave at the atomic scale. At this scale, objects behave in ways that defy our everyday intuition. Concepts such as entanglement, superposition, interference, they contribute to making this a weird and wonderful science. So when we talk about quantum computers, those are computers that operate based on the laws of quantum mechanics. And that is in opposition to conventional computers. We also call them classical computers. Conventional computers, like the one I'm using today, it operates according to the laws of the 17th century classical mechanics, also called Newtonian mechanics. And a quantum computer in a sense is an upgrade because it contains also these classical mechanics, but also will take advantage of the laws of quantum physics to encode information and to process information. Here we're talking about the quantum internet, and that is yet another quantum aspect. This is not a replacement for the conventional internet. This is an additional level of infrastructure where devices will be connected, and these devices can be conventional computers, they can be quantum computers, they can be some quantum devices that have a certain quantum capability, and they are also able to communicate using quantum computation.
That's a fantastic definition, and before we go any further, I introduced you by name, but help us understand who you are, because you all do fascinating work, and tell us a little bit about you.
Okay, thanks. I'm a professor in the Department of Mathematics and Statistics at the University of Ottawa, and I hold a university research chair in quantum information and quantum cryptography. So I am looking at the aspects of security and cybersecurity related to having a quantum infrastructure. How are we going to take advantage of the quantum communication and quantum computing capabilities? And also what are the limitations and threats related to that?
Thank you. Christoph, I think this would be a fascinating panel, no matter what the news is. Even in a news drought, this would be a really interesting conversation. But we have some kind of breaking news, especially about the investment and the budget that Canada will devote towards a national quantum strategy. Can you tell us a little bit about this news, and what does a national quantum strategy mean?
So yeah, this was very exciting news just yesterday with the federal budget announcement that now Canada, like many countries around the world, now also has officially a national quantum strategy. So the government says they want to spend $360 million over the next 7 years and the statement was to launch such a strategy. So I think there might be additional funding going forward. And they mentioned different things. I think there will be a research side to it. There will be a training side to it. There will be funding for companies, because there is a sort of burgeoning startup and ecosystem, somehow quantum ecosystem in terms of companies. So it's very exciting. I think that many of the details are still to be defined, but it's certainly good news for the quantum community in Canada, and I think for Canada.
And do tell us a little bit about yourself.
So I am a professor in the Department of Physics and Astronomy at the University of Calgary. We also have an institute here. It's called the Institute for Quantum Science and Technology. So I'm in that also. And my expertise is more on the hardware side. So we think about how to build this quantum internet, and its components, things like quantum memories, quantum transducers. We think about how to, transmit quantum states from one location to another over long distances, things like that.
Thank you. Francesco, Christoph mentioned a lot of the opportunity that comes with developing a national quantum strategy, as well as the budget, the investment here. I wonder if you could help us understand the innovation environment. What does it look like today, and what does an investment like this portend for the future?
Sure. So maybe just by way of background as well, my name is Francesco Bova. It's a pleasure to be here. I'm an associate professor at the Rotman School of Management. And I'm also the lab economist and academic lead for the quantum stream at the University of Toronto's Creative Destruction Lab. And so, the program has been in effect for 4 years. And we take seed stage companies that are trying to innovate in this particular space, that have domain expertise in quantum. And it's a mentorship-based program. We try to give them advice to make them massively scalable. And I think we've had an impact on the global ecosystem, and in particular in developing these companies in the Canadian landscape. And so I think historically, relative to other countries, we have developed an incredible ecosystem for quantum startups in this country. Vancouver and Toronto are frequently mentioned as cities that are hubs for the development of quantum startups. Sherbrooke and Quebec as well. Calgary, I think you could also include as well in that, and anything really in the Toronto-Waterloo corridor. So we've historically done very well. A lot of innovation with respect to quantum communication. Some of the original protocols, the BB84 protocol, was developed by Canadians. We've developed quantum internet in Calgary. We're looking at developing the first commercial quantum internet in Canada via Xanadu, which is an alumni of the CDL cohort. So, globally, I think we've been a first mover. So in a way, you can think of us as maybe an incumbent globally. And so it's great to see, this additional financing coming from the Canadian government. It's also interesting, though, and I think Christoph alluded to this. Governments globally are also catching up in terms of their funding, and I think that's as a result of the underlying science becoming more mature. We now have quantum computers. We still don't have a fully fault-tolerant quantum computers. We've got these noisy quantum computers that are imperfect, but we've got companies that are interacting with these quantum computers and are creating value, right? Either by generating quantum-inspired solutions or using hybrid models. So it's been interesting. I would say in the last 4 months or so, we've seen, globally, kind of the spigots of capital have been turned at various federal levels in terms of investments into this quantum infrastructure. And so while I think we've historically always been a first mover, I think we have to also be conscious of the fact that other countries are now also investing heavily. But certainly our ecosystem here is certainly relative to the size of our population, I would say on a per capita basis, is second to none.
Francesco, you mentioned a number of terms that I kind of want to stick a pin in and come back to, but kind of sticking with the premise of our discussion, John, and thank you, Francesco, for introducing yourself. John, I wonder if you could introduce yourself and help us kind of understand this balance of the promise and perils, the dangers versus the opportunities of quantum computing and the quantum internet.
Absolutely. Thanks a lot, Dan. Thanks for the entire panel for joining us. I'm at the Munk School of Global Affairs. I'm a professor. I work on national security and strategy issues. Most of my research is on information technology and cybersecurity issues. And everybody knows that information technology is incredibly important for economic and military power. Therefore, a technology that has the potential to kind of fundamentally rework the technological and scientific basis of information technologies really has the potential, or at least there's a belief that there's the potential to really have to create opportunities in the economic realm, to create opportunities in the military realm. And if you do that, you also end up creating threats. Let's just kind of jump to the elephant in the room, or the panda in the room, if you will. China has really embraced quantum technologies as a core plank of their economic and military modernization strategy. And on the military side, if you think of all of the things a military might do, it wants to sense the world, it wants to compute the information that it gathers, and it wants to communicate with all of its units. Quantum technologies can potentially enhance all of these things. It can enhance sensing, it can enhance computation, and it can enhance communication, which is sort of what we're talking about today. So China has become very excited about this technology as a potential of leapfrogging the United States and gaining a comparable, if not, potentially a dominant position in regional or global geopolitics. So given that dynamic, that of course then prompts counter investment in North America and in Europe. So some people are talking about kind of the beginnings of a quantum arms race. And I want to kind of heavily caveat that kind of phrase, right? I mean, there are lots and lots of uncertainties that surround it, but it's the interaction of this bleeding edge scientific frontier with potentially big economic and political consequences that I think has really caught the attention of senior policymakers and started to open up the coffers for investment in this area.
I love, John, that as soon as we have an innovation, no matter what the innovation is, we definitely jump to the weaponization of the innovation right away. But I do want to talk about the leaders, the geopolitical leaders in quantum technology and quantum communication and the potential cyber components of this. And I know you're an expert in that as well. But let's, again, I want to stay kind of basic here with a few more definition of terms. What do we mean when we're talking about the actual quantum internet? And I know you said a moment ago that this isn't the exact same. It's not like we'll have quantum Zoom meetings, but we've given a lot of examples of what we might be able to do with the quantum internet, but what exactly is this quantum internet? What is quantum communication? What are qubits? And when do we anticipate this technology becomes a reality for businesses and consumers? And I'm kind of leaving that open to the panel. We'll come back to specific answers or specific questions in just a moment, but anybody who has a good answer to that, please stick your hand up.
I have an analogy to share. The quantum information, that means that when we talk about quantum communication, it means that we're able to send encodings that are using the properties of quantum mechanics. So if I compare that to conventional or classical information on my current computer, it's encoded at the basic level. If you go down deep into the hardware, the basic level is that the information is zeros and ones. So you have a sequence 0, 0, 0, 1, 1, 1, and that's a character, and that's how you present a letter, and then you build up and you build software based on this, etc. So at that same fundamental level for quantum information, it's something different. It's called a qubit. That's the basic unit of information for quantum computers. And that's at the atomic level, something that's going to behave according to the laws of quantum mechanics. So for me, conventional information, it has this property that it's easy to copy. It's always possible to keep a backup copy of anybody's conversation, of anybody's email, of digital music. It's easy to share, etc. But at the quantum level, things are completely different. And quantum information qubits behave a lot more like physical objects, like an apple, if you will. So this apple, I can taste it, but it's going to leave a trace. Anybody will be able to see that the apple has been modified. I can share it with you, Dan, but we'll each have a piece. We will not be able to each have the entire apple. So that those types of analogies, they actually go a long way to understand the potential of quantum communication, and that is that we're able to reproduce this physical properties of being able to detect tampering, and that leads to quantum key distribution, also called quantum cryptography, and all sorts of other aspects that are really useful for security in quantum communications.
That's a fantastic analogy. And often when we think about the potential perils of quantum on the very simplistic level, we think about encryption. And I know I've written stories about how maybe quantum computing could get rid of all the algorithms we've used to encrypt our passwords. But that feels a little reductive and a little simplistic. So I wonder if we could kind of talk about the potential of quantum for cybersecurity before we talk about the potential cyber vulnerabilities. John, I know this is an expertise of yours. It's an expertise of everyone on our panel, but I wonder if you could talk a little bit about how cyber might be enhanced by quantum computing.
Sure. So as you mentioned, Dan, a lot of the algorithms that we use for our encryption, and this is for financial transactions and government communications and personal privacy, are encrypted by an algorithm which is generally very, very strong. But if a quantum computer was ever built, and that may be in 5 years or 10 years or 20 years, it might be able to decrypt that data in a matter of hours or days, rather than many times the age of the universe. Okay, so that's a problem. Obviously, it's a problem not just for live communications, but even things that might be stored and maybe valuable for 10 or 20 years. Maybe intelligence agencies are collecting that today, so that when a quantum computer is available in the future, they'll be able to start bulk decrypting that. So you have two alternatives. One is to use the strange properties of quantum mechanics that Anne just discussed, which allow you to encrypt data in brand new ways. And the quantum internet would perhaps leverage these principles. And then another alternative would be to use different classical algorithms that maybe are not as easy to attack with a quantum computer. And that's something that the global cryptographic community is really, really working hard on, and the standards process in the United States is quite mature to come up with so-called post-quantum encryption. So the peril, again, would be that security as we know it could be compromised by quantum computing, but the same technological development allows even more secure protocols.
Francesco, I have stood in front of a quantum computer. I have taken pictures of a quantum computer, but I know this isn't an actual quantum computer, just replicas of what one could look like. What is a quantum machine, and how is it different than a current quantum machine? And when will these be in live use?
So I think even the scientists might be reluctant to give you an expectation about timeline. So I think maybe I'll also defer in terms of expectations. But let me maybe argue why even in their current state, there's value investing in kind of the quantum startup ecosystem. And so I'd also answer your other question, maybe not on the technical side, but why might a quantum computer be a threat to security, and why might it provide opportunities for a variety of different companies or academics? And as John alluded to, right, a fault-tolerant quantum computer can solve problems that are intractable for current classical computers, right? Instead, a classical computer might take multiple times the age of the universe to solve a problem, and we can solve that in a comparatively trivial time. With the fault-tolerant quantum computer, as a result of the quantum phenomena that Anne had discussed, superposition, entanglement, a variety of other quantum phenomena. And so that's the threat. And so first of all, even though we might be years away from developing a fault-tolerant quantum computer, there's still an incentive to start building a quantum internet today, right? Because there's kind of the transition to this post-quantum state where we've got improved security using either quantum or classical solutions, changing the current infrastructure and changing the current paradigms, it's going to take a long time, right? So, and this is a global problem, right? Because a lot of these protocols are used globally. So even if, let's say, for example, it's 20 years away to create a fault-tolerant quantum computer, there's an incentive to start changing that infrastructure, that security infrastructure today. And as a result, that's why I think you're seeing a lot of governments investing into changing these protocols and infrastructures. And in fact, we're seeing private capital going into private industry to change some of these protocols. So that's on the threat side. On the opportunity side, as we've mentioned, we don't currently have a fault-tolerant quantum computer. We have these noisy intermediate quantum computers. I suspect that's what you've seen, Dan, up until this point. I'm not sure which company it was, but I think they would probably all classify themselves in that category.
They would.
So,
they do. Google and IBM both are trotting them out right now.
Right. So so they're as with all quantum hardware startups, they're trying to improve the quality of their qubits. I'm sure increase the number of qubits, try to reduce things like measurement error, noise, to mitigate issues with decoherence. So and all of these hardwares are improving. But what we found, so a number of the software, the application startups that have come out of our lab, they've just been experimenting with these noisier intermediate quantum computers, and have been able to generate value by deriving quantum-inspired algorithms that they can run classically. And most recently, I would say this is maybe even the last 6 or 7 months, even using these noisy intermediate computers in a hybrid format where they solve the majority of the problems they're working on classically, using, for example, the laptops or supercomputers that we use currently, and then use quantum computers, even in their noisy state, to solve other facets of the problem, very specific parts of the problem. And then they benchmark the results against other sorts of classical benchmarks, and they found improvements, in certain verticals like finance, materials discovery, for example, and advanced manufacturing, amongst others. So interestingly, even though we might be years away from a fully fault-tolerant quantum computer, there are incentives to invest in this space, both from a security perspective and invest in in developing a quantum internet today from a security perspective, and then also investing in applications that would make use of quantum computers today. And so I think that's the state of the economic landscape currently.
Francesco, I want to come back to you in just a moment and talk a little bit about the state of the commercial landscape. But Christoph, I wonder if you could help us understand the state of the academic landscape right now. Where is major research taking place, and what types of breakthroughs do you see happening?
There's really a lot of different things. So there's certainly the progress on the quantum computing side that we already alluded to, and you mentioned companies who are trying to build quantum computers. They are reaching a certain scale. They are seeing 50 qubits or something like that. They are seeing major investments in the hundreds of millions of dollars in some cases. So there's certainly a lot of dynamic happening there. There's also a lot, and a lot of that is in North America, I should say. Then there's also a lot happening on the quantum communication, quantum network side. But there, the focus, I would say, has been in China and to some extent in Europe. North America is a little behind. So like in China had a quantum communication satellite, for example, the first one, and they showed that they can send quantum information over like 1,000-kilometer distance, with the help of this satellite, things like that. They also have like a pretty highly developed network already of quantum key distribution, where really things in North America are not comparable to what they have done right now. And there's sensing too. People are working on, John mentioned, various like quantum sensing applications, and there's some startups in that area too. So there's really a lot of different things.
I kind of want to stay on the topic of academics, before we go back to the commercial application, this is for the entire panel. When you kick back with your Kindle or your iPad and you're reading papers, who are you reading and what papers are top of mind for you right now? And let's start with you. What academics, who is a leader in the field and what are they writing?
Okay, well, that's a very broad question. Yeah, in the cryptography world, but this is very theoretical. Things that have been going on recently is work where you actually you can use quantum devices to create things like certified randomness and like perfect randomness based on the laws of quantum mechanics, or things like delegated computations where you could outsource a quantum computation to the quantum cloud and take advantage of that cloud quantum computer in a private way. And breakthroughs recently are things related to device independence. So you can actually, you don't even have to trust your quantum device. So as a cryptographer, I'm super paranoid. We talked about noise. Well, in a cryptography world, noise will be attributed to an adversary. So there's always somebody trying to eavesdrop, trying to interfere. And the device independence takes that paranoia to the maximum, where even you suppose that the quantum device that was purchased could have been manufactured by a malicious entity. So how could you even do anything useful with that? Well, actually you can. And like that's kind of mind blowing that you don't even have to trust the quantum device, and you can still get this private randomness, for instance, or the delegated computations.
Thank you. And I'm kind of using this as a reference for the real nerds in our audience for follow-up reading. John, you talked a lot about some of my favorite topics, which is geopolitics and cybersecurity. But really, what I'm very interested in are the global leaders in quantum. And are there things that we need to watch? Are there signals? Are there flags that we need to watch to see whether one leader is accelerating further beyond the capabilities of the rest of the world?
Well, I'll let Christoph speak more to kind of the technical indicators, but one thing that people kind of in the China watching community, or any kind of geopolitical analysis, we look for top scientists who are publishing a lot and then stop publishing, and that's often a signal that they are continuing to work, but they're not publishing public anymore because their research has gone dark. That's always something that happens at the cutting edge. One thing that's interesting about quantum, right, is that it's a tremendously kind of dual use technology, right? It's being driven both by government investment and by this flourishing, civilian information technology economy. So, one reason to make sure that you have that flourishing economy is that you don't want to get caught by surprise by having it be a purely kind of government on government thing. But
Christoph, and I'm sorry to cut you off, John. We are running a little low on time here, although I think I could talk with each of you forever. Christoph, what are some of the technical flags that you look for?
Could you specify what you mean by flags? Like, you mean what's happening right now that's exciting? Or like what?
Well, beyond what's exciting, if we look at the geopolitical landscape, are there indicators that you look for to say one actor is accelerating beyond another actor? And we'll talk with Francesco in just a moment about some of those same commercial flags and why it's so important to invest in this ecosystem. But before we get there, help us understand some of those technical indicators.
I mean, I mentioned some of that before briefly. So I think I am a little concerned that in North America, we are falling behind on the quantum network side of things. I think we are doing okay on the quantum computing, but like on the network side, like the satellite, I think that's a bit of a Sputnik moment to my mind. Like if other people launch the first satellites, that's usually something where you should wake up. We actually have a Canadian satellite mission planned now, to be fair, but it is much smaller and later.
I love that Sputnik metaphor, and that might be kind of where we're at right now. Francesco, why is it so important to invest in this ecosystem?
So maybe I'll look at investments two ways: investments from current companies that maybe should look at experimenting with current quantum hardware, and then in just investing in terms of capital as well. Um, and so I think one of the benefits of just experimenting with the current quantum hardware is, so in the long term, you'll be quantum ready, right? At a point in time, if we get to a point where we've got a sufficiently coherent quantum computer, but even in the short term, right? And so this is coming directly and anecdotally from a number of companies that we've worked with. They've just been able to derive, these quantum-inspired algorithms that they can run classically just by experimenting with quantum hardware, right? So just it's simple cost-benefit analysis, right? I've got a technical R&D team, right? And I assign them to work with quantum hardware as opposed to another type of platform. So there's an opportunity cost there. And what I'm saying is, even in the short term, that opportunity cost has been outweighed by the benefit of generating some of these quantum-inspired algorithms. So I think maybe the time is now to start experimenting with quantum hardware for maybe companies that haven't had a chance to do so up until this point. There's both short-term and long-term benefit. And then why should companies invest? It's because there's a lot of growth here, right? I mean, I think the underlying hardware is getting to the point where it's usable, again, in a hybrid format or in a quantum-inspired means, such that you can create value, right? In the case of creating a quantum internet, even if we don't have a fault-tolerant quantum computer for 20 years, we need to start developing that infrastructure today, because the transition period could be 10 or 15 years, right, to kind of get the change made globally. So I think there is a compelling argument to be made, and just again anecdotally, right? I think there's an article in Nature, I think last November, and they had an appendix with the amount of private capital that's flowed into quantum. So this doesn't include publicly traded companies. It doesn't include federal funds. It doesn't include, for example, the money that Germany or China or the US or Canada are pouring into this, into startups. But as a very conservative lower bound, I think it was like $1 billion had been contributed from private capital, right? So very low, right? When you think of the market cap of some of the companies that we have on publicly traded exchanges, that's it's barely measurement error. And so that flow of capital, though, has increased, I would say, exponentially over the last year and a half. And I think it's a function of the underlying technology becoming more mature.
It's fascinating. So I wish we had more time for this conversation, but we do have time for fantastic audience questions, and a few have already come in. If you have a question for our panel, please don't hesitate to submit it. And I don't want to say everyone will be available on Twitter, but if you are willing to answer questions on Twitter, give us a shout, and I'll share your Twitter or social media in the chat at the end of this conversation, because this does deserve a much longer dialogue. So we have a few that have already come in. A great question from Michaela. And again, for our entire panel, please just unmute and jump in to answer these questions. Question from Michaela: how does one work with quantum hardware? It's a basic question, but a really fundamentally important question. Anyone want to volunteer to answer? Christoph?
So there are different ways. I guess I can interpret the question in different ways. Like, for example, some companies now offer the possibility to run sort of quantum programs on their quantum devices, which, as you said, are still noisy and imperfect and so on. But like one can try them out and do things on them. And many experts are doing this now. There's many people who use that to perform little experiments sort of in the cloud. So that's an interesting way. I think Francesco was talking also about companies now using them for applications. I'll maybe let him speak to that. I think he knows better what companies are really doing right now.
Yeah, so I think, and just to kind of echo Christoph's point, I think that's exactly what they're doing. So most I think probably all quantum computers are going to be cloud-based. In some instances, quantum computers need to be, frozen to almost absolute zero to get the quantum mechanical effects to arise. So this is it's not like a laptop, right? At least we're not at the point currently where you would sell a quantum computer to like a downstream customer. So almost all the work is done in the cloud. And I can think of most of our technical partners at CDL. I think there's probably an opportunity, maybe not for free, but I think there's opportunities to just interact with their hardware over the cloud if that's something that you would like to try. And so that's what companies are doing, right? And in many cases, looking at these really big optimization problems. So kind of the classic example that I could give is what we call the traveling salesman problem. And I think it kind of illustrates the potential of quantum. So you've got a salesman that has to go to starts in a home city, has to travel to a bunch of cities and then end up in the home city. Presumably they will make the same revenue, irrespective of the route that they take, but they'll minimize their costs by taking the shortest route. Okay, so they'll maximize their profit. So this is an optimization problem, comparatively easy problem to solve. If there's few cities, it gets exponentially more intractable the more cities are involved, to the point where maybe classical methods can't solve this problem, but perhaps quantum computers can solve this problem. So you can think about like a logistics problem for corporate Canada, with with an exponential number of possible routes that you could take. This is where one of the places where quantum might make inroads.
Another great question from Victor. In your view, for our entire panel, how can the government in Canada, the government of Canada, best invest in quantum? And maybe, do you have an answer?
Well, from my point of view, it's training the next generation of people who are going to be involved in quantum. We need the brains, we need the people to be able to be quantum knowledgeable and to be able to take on this challenge. We're a great group of scientists already, but if we're seeing a growth in this area, then that needs to be supported by the people that will be doing that work.
Another question that
can I add something?
Please do, Christoph. Please do.
That for sure is an important component, as is research and so on. But I think one thing that's a little maybe underemphasized still is the government as a first customer. I think the government can have a major role there in principle, to develop this infrastructure, both for quantum computing and also for this secure communication. I think that would be a very good way to help Canadian quantum companies too.
Another great technical question from Scott. The panel mentioned that quantum computers need to be kept really cold, near absolute zero. Is there any research being done to look at room temperature quantum computers?
Yeah, there is some, and I'm doing some of that myself, but it is further off for sure. I mean, to some extent, you could argue that trapped ions are at room temperature, but they are cooled in a different way. They are trapped and so on. But like if you imagine room temperature in a solid state or something, that people are thinking about it, but it's harder and it's going to take a bit longer to get there. But I don't think it's impossible.
A question from Dante about quantum hardware and safety and trust. This is a great question, actually. Is there any idea that allows you to securely use a quantum device if you don't trust the manufacturer, which I think is incredibly important when we think about the importance of the supply chain with classical computing. This is going to be incredibly important when we think about the challenges, how difficult it is to develop quantum machines and how few manufacturers there might be.
Yeah, I can speak to that a little bit. I think it actually echoes some of the things I talked about were like I call it device independence is one of the formal words. So in that case, we're able to, it's kind of like a cross interrogation. Say you have two untrusted devices and you separate them in a way that due to relativity, they actually cannot communicate, and you send them as a user, you send them challenges and check their responses. That's one way to actually be able to gain confidence that the computations are being done correctly or that the randomness is really random, etc. There's another way, which is a bit of a bootstrapping thing. So maybe you don't trust the full quantum computer, but you trust a small quantum device and you've really tested that. Maybe you created that one yourself, and your small quantum device is going to do something trivial, but still very important. And then you can kind of bootstrap that to be able to trust the entire quantum cloud via the quantum communication. And there's yet another one, which would be to use a quantum secure computational assumption. So we talked about factoring, but there are alternatives to that. And there are ways to mesh. These are very much at the theoretical level right now, but there are ways to mesh some untractable computation problem, and then the quantum computer would have to break that problem if they were going to cheat and return a incorrect answer without you being able to detect it, for instance. You're on mute, Dan.
The perpetual mute problem. A question about blockchain. I know that Bitcoin is hot again and NFTs are hot, and this is kind of a consumer look at the blockchain. But I think that when we look at encryption, blockchain is kind of important, or at the very least, it's very interesting. So we have a question from Stephen who asks, will quantum computing be a threat to blockchain technologies and cryptocurrencies?
Anybody else?
Are there crickets here?
I don't want to hog the conversation, but yes to certain things. So things like, what's it called, mining or whatnot. So we can actually speed up some of these computations that actually end up breaking the blockchain using quantum computers, but they're using what's called Grover's algorithm. But there's a way to mitigate that. So that's actually a topic of current research of what are the parameters that we would have to include in the blockchain technology to mitigate the quantum attacks and also all other possible quantum solutions.
We have a question once again about hardware from Li Dong. This is a fairly long question, so I'm going to condense it a little bit. But he says, to build a quantum network, a quantum communication network, we need satellites or devices that can communicate with each other over a long distance. So his question is, and again, this is a long question that I'm condensing. I hope I'm doing this, condensing it properly. But what type of maintenance will the quantum internet take? I assume this means, will there be specialized jobs? Will there be specialized hardware? And what hardware goes into this network?
Yes, I think it will be quite a complicated thing. I think satellites will be definitely one component. The satellites will maybe send entangled photons down to the ground or something. But they will, or they will receive photons from the ground and do interesting measurements on them up there. But there will definitely be important components on the ground too, sort of networks that exchange quantum information it's all in the form of photons. The long distance connections, I think, will always be light-based. And then there is nodes that can do processing and storage and so on. So just like the classical internet is really a very complicated beast now. The quantum internet will be even more so, I think. But these are important components.
Another very a question that we've heard quite a bit, but I think is really important, from Peter. He asks, can you please explain quantum supremacy, and has this been achieved?
We don't use that word anymore. It's now quantum advantage. Quantum supremacy, obviously, it's got some dark undertones we don't want to deal with, but yeah, right. So Google has built this machine called Sycamore with 53 qubits. And when they announced that they had solved this very, very particular problem, they said that the fastest supercomputer in the world would need 10,000 years. And then IBM came back and said, no, we can do it in 3 days. But that's still not 3 hours, which is what Sycamore was able to do. And then the Chinese came back with a very, very different machine, which actually used lasers and ran at room temperature. We're also able to solve a problem very, very quickly. So this kind of threshold where quantum computers can solve things faster than other computers has been passed. But right now, these are kind of like scientific lab problems, right? We don't actually have quantum computers that are solving real world useful problems, but this is kind of a prototype that shows the art of the possible.
I love this idea of the art of the possible. John, before we jump into the next question, you alluded to this change in jargon or the change in language. And I think I have an understanding of what you were referring to when we stopped using the term quantum supremacy. But can you dive a little more deeply into that and explain this change in language?
Oh, I don't think there's anything very sophisticated here. Just you know, in the context of the racial reckoning that we're going through, I mean,
Yeah.
something that sounds like supremacy doesn't sound so good. But there's this kind of technical question of when is a quantum computer outperforming a classical computer? You need to call it something. You know, and supremacy sort of implies that you really have this dramatic advantage. The Chinese have an even more extreme term that they call quantum hegemony, right? So the country that achieves you know, massive quantum power will be able to outcompute and outcompete all of its rivals. But this just speaks, hey, there is a, you know, mathematical computational advantage that's been achieved. Where can that go? That's the question, right? And a big part of the quantum internet is, you know, we need to build it and start building these prototypes to actually understand what was possible, right? I mean, early computers, right? So ENIAC and Colossus, they filled a room, wires hanging out all over the place. That's kind of what quantum computers look like today. And, you know, the president of IBM, Thomas Watson, said the world's only going to need, you know, 5 or 8 of these machines. Well, you know, just couldn't have foreseen what was possible. So there is enough reason to believe that we can do some cool things, but we have no idea what that's going to look like at scale until we really start, you know, putting it together.
John, I think that's really important, especially tying 2 points together. We don't know what is possible, and the language we use now at the beginning of an innovation is really important. So we don't bake in terms that might have either overt or latent racist, sexist, or otherwise demeaning language. That we know the power of language. Language can divide people, and when we bake language into technology, there are consequences. Maybe that's kind of a sidebar conversation, but I'm really glad that you brought that up, John. And I do want to remind the panel, we do have a few more minutes left. So you can submit any more questions that you might have using the QA function at the bottom of your screen. Dan has a question that is about power consumption. Can the panel compare power consumption used by quantum computers relative to what we're doing now?
I don't have good data on that. I think I have to be cautious because there is the in principle and then there is the in practice. I think that in practice the power consumption is quite high right now. In principle, I think it could be low because it's in a sense reversible computation. You know, there is not these fundamental reasons that we need to use a lot of power. But I think in practice, we are using a lot of power right now to run these computations.
Bernard has a question about quantum physics. He writes, my recollection of quantum physics is that the mere attempt to measure a physical state changes that state. So how can a machine which operates under this premise provide a unique answer to a given state of inputs, given set of inputs?
So there is a simple answer and then a complicated answer to it. Like the simple answer is you just don't measure it until the end. Now, of course, in practice, that doesn't quite work, and you have to do something more sophisticated. That's called quantum error correction, where you just measure, you know, certain things, you know, just in the right way, and you correct the errors that happen and so on. But like basically, you try to effectively not disturb it while it is doing its thing, and you only check at the end. And that's hard. That's why it's hard.
Anyone else? All right, Ron has a question about the economics of hardware versus software. He writes, will there be more money to be made in hardware or software or services? If the latter, why bother with the hardware?
Well, I think, yeah, it's hard to conjecture, I guess, what kind of future profit margins will look like in either of these spaces. But we need the hardware to have, I think, to have the software, right, to have these applications that are run on quantum tech. So the hardware development is important. The technology roadmap for the hardware is also, it's a lot longer. Like, you know, you can think about D-Wave, I think, which is based in Vancouver. I think they've been at it for almost 20 years, and they might have been one of the first quantum hardware companies in the world. So it's a lot longer. So in a way, we're comparing apples to oranges. You know, again, I'm not sure if the software is possible. There are apples to, thank you, Anne. We didn't coordinate that. That was fantastic. I mean, without sufficiently coherent hardware, you know, kind of the software is very much a second order thought. But once you get to that point, the development of software applications is a little quicker. And you've got, it looks like you've got another point to make.
Yeah, I'm a software person, and if it hadn't been for software, the 1995 discovery of Shor's factoring algorithm, we wouldn't be here today. So the software has the tremendous potential of like having this foresight of what we can expect in the future, and we need to develop that now to know how we can guide the technology.
So this is a good point. I think I probably narrowed my comments to applications of quantum computing. So I guess without the quantum computing, there really would be applications, but you're exactly right.
Nick, no, go ahead.
I think at this point, it's hard to tell because we've got competing quantum architectures that are being developed. It's hard to tell, you know, which one is going to be more dominant in the future. So I mean, it's hard to tell, I think, ex ante, you know, where the value is going to arise.
Well, I think on kind of the topic of architecture, Nick writes, globally, who is or who should be taking the lead in terms of creating the standards and protocols related to quantum communications? And I might add to that, how are these protocols being developed?
So there is actually, I mean, there are standardization processes in course as we speak. Like in Europe, there's something called ETSI. The United Nations has a process. I think it's called the ITU process. So there are like experts, you know, talking about these things and trying to set standards. For example, for quantum cryptography. So that's certainly an important area that will help. I think for wider deployment of these solutions, it will be important to have these standards.
So internet pioneer David Clark, he's got this wonderful phrase. He talks about the apocalypse of two elephants. And the first elephant is when everybody is suggesting all of these standards for various parts of the software and hardware stack. And the other elephant is when everybody embraces and commercializes that, right? And so the question is, you got to find that sweet spot where you've had all this creativity and experimentation to get the right standard. Because when you get into the next batch, right, you're going to get locked in. And if you get locked into a bad standard, that could be inefficient, it could be insecure, all kinds of bad things could flow from there, right? I mean, we're still in IP version 4 rather than 6, right? And that was many, many years ago because that standard gets locked in. So I think this is a really, really important question. Even though the US NIST process is well down the road and coming up with these post-quantum crypto standards, right? It's going to take a long time to finally get those implemented and authorized and diffused throughout the world. In the meantime, you know, you may have a quantum computer and these standards available, but people haven't fully upgraded. And this brings up, I think, a really, really important part that I want to emphasize. No matter what we talk about in terms of the state of the art, all of these machines and all of these pieces of software have to be implemented in classical human organizations, right? And there's no patch for human stupidity, right? So you could have the most amazing crypto, but if it doesn't get implemented correctly, we're still going to have cyber insecurity and all kinds of interesting problems. So in many ways, quantum is just going to make our existing situation even more complex and exciting and fearful and full of opportunity and threat.
Which I think brings us back to the training topic, right? It's really important, I think, for enough people to be aware of these things and understand these things at some level, you know, so that we can prepare for this new world.
I want to remind our audience we have just a few more moments. So if you have additional questions for our panel, you can use the QA feature at the bottom of your screen. Maybe going back to the beginning of our conversation and drawing parallels to the classic internet that many people kind of remember taking shape around the Mosaic browser. Piero writes, when are we going to have a Mosaic moment for quantum technologies? Now, the Mosaic browser was one of the first commercial web browsers that helped with the explosion of the World Wide Web. It helped consumerize the World Wide Web. So I think what he's asking is, when will we have a parallel moment for quantum computing?
It's not clear, I don't think.
Shrugs, shaking of heads. So we just don't know. And maybe the answer to that is there isn't a parallel. Is that a little more accurate?
Well, I mean, you could imagine several trajectories, and one is quantum computing and quantum networking remain highly, highly specialized infrastructure for particular kinds of computing, particular kinds of cryptography. Kind of the guts of the internet will have some quantum components. And, you know, that'll be kind of rarefied scientific infrastructure. And then there's this alternative trajectory, right, where we all have a quantum computer in our pockets and it's doing, you know, applications that we've never imagined because we didn't have the ability to take, you know, Anne's cryptographic apples and send them around the world in, you know, different, you know, inconceivable ways. And then everything in between. So I guess that's what I'm getting at, is there's just this fundamental uncertainty on what the social, economic, and national security trajectories of this is going to look like. But that means that it's really, really important to start talking about this now, right? Because, you know, some of these societal and economic questions were not as live during the kind of the early moments of the internet as we know it now. And therefore, we're dealing with all kinds of security problems that weren't built in at the beginning.
Elena asks, is quantum computing in need of new high temperature superconducting materials that can be developed by chemists?
Sure, certain approaches to quantum computing, I think, would benefit from that. Like superconductivity plays a role in some of the prominent, you know, approaches to quantum computing. So that's very welcome, I think.
And Alex asks if there are leading methods of developing or building hardware. His question is a little longer, so I'm condensing it. But I think the development of hardware is pretty fascinating, especially since we can conceive of what a traditional computer looks like. It's harder to think about what a quantum computer or a cloud quantum computer might look like, or how one might be manufactured.
Yeah, I mean, there's a few like established approaches for sure. It's not really clear, as I think Francesca said, who is going to win the race in the end. But there is, yeah, superconducting qubits, trapped ions, photons, various spins in solids, and so on. There's still a number of approaches that I think have a chance. And then for the communication part, it's pretty clear that somehow you have to interface with photons.
Well, speaking of interfacing, and this might be one of the last questions we're able to get to, Ron asks, how will ordinary users gain access to quantum computers and quantum technology? Francesco, I know you mentioned that, hey, you can use applications that are in the cloud or you can rent servers. Are there other methods that regular people can interact with or use or write apps for quantum computers?
I think with all of our technology partners, I believe it's all cloud-based. You know, I think in certain sectors, I think some companies are developing their own in-house quantum computers. There's a lot of opacity around that, so I don't know how far along that's developed. To the best of my knowledge, most of the interactions currently would be cloud-based. I'm not sure if Anne or Christoph or John have any other insights.
Also, if you are really, really worried about security, you can buy a quantum key distribution system right now. You know, there are companies that will sell you one, so you could use that too, depending on your interests. But they are expensive.
We have 1 minute left, and I will ask you, the panel, one last question. I'm a journalist, so for reporters, for writers, for TV producers who are covering this, what is the best way to discuss quantum computing and the quantum internet without being reductive, but in ways where we might have limited column space or limited time, that best communicate quantum ideas in a very helpful way to an audience that might not understand everything that you understand as experts?
So I think the way that I might explain it to a business audience is that we've got these large intractable problems that are tough to solve for classical computers, but that may be solvable for quantum computers. That represents a threat because these large intractable problems form the foundation of a lot of encryption and cryptography, but that also presents an opportunity because companies have a tough time solving these large intractable problems. And so that's the way that I would try to frame it, maybe for an audience who are not domain experts in the field.
And again, for the security part, I would say that quantum poses threats. Quantum computers pose threats, but then quantum physics also offers solutions. So.
That's wonderful. Well, thank you all for joining in. I understand that we have a fairly sizable audience, and I understand we didn't get to all of your questions, but we do appreciate you submitting them. Anne Broadbent, Francisco Bova, Christoph Simon, John Lindsay. You all are true experts, and I appreciate your insights, as does our audience. My name is Dan Patterson for CBS News and the University of Toronto. I want to thank everybody for joining us, and we will see you again real soon.